Here we derive the boundary layer equations. So for this derivation, we will assume the flow to be steady. We'll assume that the flow is steady, incompressible, and for simplicity, we will assume a 2D planar geometry. And now let's assume that we have this our airfoil or our profile. We consider a very simple, our generic flow situation with a uniform flow of magnitude u coming in the x direction. The fluid is of density rho and of viscosity mu. Now, if we look about the boundary layer, we have to think about our length scale. And so we have two, in that case, characteristic different length scale. There is the usual one, so we start with a characteristic length scale in the x direction. And that characteristic length scale in the x direction is really is going to be the length of our profile, L. Right? So that's the characteristic length scale x. And then we have, in the y direction, another characteristic length scale, and because we're looking at the equation inside of the boundary layer, this is going to correspond to the thickness of our boundary layer, delta. Right, so delta here is our length scale in the y direction. And so what we do is we will take to simplify the Navier-Stokes, the momentum equations, we'll take the momentum equations and we will non-dimensionalize it with the different scales that we have. So let's start with the scale for velocity. The velocity in the x direction simply scales with the velocity of the incoming flow, which is u. So u here is going to be our velocity scale. So we can write u is equals to capital U times u tilde, where u tilde is non-dimensional. In the x direction, we're going to rescale our x coordinate, and that, of course, will use the length scale in the x direction, which is L. So this is going to be equal to capital L times the non-dimensional x. When we non-dimensionalize the y position, we will non-dimensionalize it with our other length scale in the y direction, which is delta. So we'll write that y is equal to delta times y tilde. We also have a pressure term in the momentum equation that we need to non-dimensionalize. And so we'll take, because we're assuming that the Reynolds number is high, we'll take that our pressure scales with rho times u squared. And the last term that we need to non-dimensionalize is going to be the velocity in the y direction, v. Now, what is the scale for v? You can imagine that in the boundary layer, the flow is going to be mostly, in this region, the flow is going to be mostly in the x direction. And so the velocity in the y direction is going to be small. But what is the scale for that? Well, to find the scale for v, we need to go to the continuity equation. So let me write it here. We have our continuity equation here, and we know that u scales with u, and we know that x scales with L. And we don't know what v scales with, but we know that y scales with delta. So the first term is going to scale with u divided by L, and the next term is going to scale with our velocity scale for the y direction divided by delta. Right? And so from this, you can deduce that our velocity scale in the y direction is going to be u times delta divided by L. So we can write that. U times delta divided by L. This is going to be our characteristic length scale for v. Our characteristic velocity scale for v, the velocity in the y direction. So we'll start with the x component of the momentum equation. I'm writing it here. I'm writing all of the terms. I'm not putting the rho du dt term because we're assuming the flow to be steady. And so let's take every single one of these terms and see what they scale with. So let's look at the first term. It scales with clearly rho times u divided by L. So it will scale with rho u squared divided by L. Let's look at the second term. We have a rho. V is now going to scale with u delta divided by L. and partial u partial y is going to scale with capital U divided by delta. Right, so that's our scale, and we see that the delta simplify, and that this whole thing now scales with rho u squared divided by L. Now let's look at our next term, the pressure term. The pressure term will scale with our pressure scale, rho u squared, divided by our length scale L. And now when we look into the viscous term, we have two different terms. The first term is the simplest one. It will scale with mu times the velocity scale u divided by L squared, because it's a derivative in the x direction. And the last term will scale with mu times u divided by delta squared. And delta squared, we have a scaling for that. Right, delta squared, we have the scaling in terms of the Reynolds number. So this scales with rho u divided by L squared times the Reynolds number, because remember that delta squared divided by L squared, or delta divided by L, scales with the square root of the Reynolds number. Now if we replace that with the Reynolds number based on the length scale L, we find that this term scales with mu u rho u L divided by L squared times nu. And when you simplify all terms, you see that the dynamic viscosity simplify, and you end up with rho u squared divided by L. So you see that this last viscous term in the y direction, so this term here, is of the same order of magnitude at this scale here as those two terms, and this is not a surprise because this is precisely how we defined the length scale delta. Right? We defined delta as the length scale over which this term here would be similar in magnitude as these terms. But what you clearly see is that this term dominates, is much larger than that term. Right? This term here does not scale with rho u squared divided by L. This term here is much smaller, and therefore we can neglect that term. And so in the boundary layer equation, this term disappears. So that's the simplification of the boundary layer equation for the x momentum equation. Okay, we continue our derivation of the boundary layer equations, and this time we take the equation, the momentum equation, in the y direction. So here is the equation. Again, we keep all the terms except the rho dv dt term, because we're assuming the flow to be steady. And so we have to scale all of our different terms. So let's look at the first term here, the term which is rho u dv dx. So it's going to scale with rho u times the velocity scale for v, which is u delta divided by L divided by d. So when we put all this together, this scales with rho u times delta divided by L. This here is our scale for v times u divided by L. Sorry, this is u. This is our scale here for v. And this here is L. So when we simplify, this term scales with rho u squared delta divided by L squared. Let's take now our second term. This is going to scale with rho v squared divided by delta, right? And v again scales with u delta divided by L. So we have rho u squared delta squared divided by L squared, and divided by delta because of the partial with respect to y. So when we simplify all of the deltas, again, sorry about that, we have rho u squared divided by L. Next, the pressure minus pressure divided by y. So it is going to scale with our pressure term, rho u squared divided by our length scale in the y direction, so that is delta. And now we have our two viscous terms. The first one is going to scale with mu times the velocity scale for v divided by L squared, and our velocity scale for v again is u delta L. So we're going to have a L cubed at the denominator. So mu u delta divided by L, 1 divided by delta squared. So again, if we simplify all of these terms, we get Sorry, I went too quickly. Here I'm dividing, it's a partial with respect to x, so I went a bit too quickly. It's going to be an L squared, so when we simplify all of the terms, we are left with mu u delta divided by L cubed. And this is our last term, so that one is going to scale with mu times the velocity scale for v. And this time we're taking the partial with respect to y, so we're going to have a 1 divided by delta squared. So all things together, that gives you mu u divided by L times delta. So now we have to compare all of these terms. And so remember what we did last time. So if we're comparing those two terms, it's very clear that here we have a 1 divided by L squared, and here we have a 1 divided by delta squared. And because delta, the thickness of the boundary layer, is much smaller than L, this term here is going to dominate between the two. And that term here is going to be much smaller. So we know that at least this term is much smaller than that term. Now, if we look at our two inertial terms, they have the same scaling, so none of them is negligible compared to the other. But let's compare our inertial term with our pressure term. So in our pressure term, we have a rho u squared, which we divide by a very small number. So this is going to be quite large. And here, what we have is that we have a rho u squared, which will multiply by a small number, divided by L squared. So this term is going to be really small compared to that term. So this one is going to dominate, and these two terms are going to be much smaller compared to that. So these two terms drop out of the equation because the pressure term dominates. So the only terms we have left is the pressure term and possibly this viscous term here. But if you compare the two, if you take the ratio of the pressure term with respect to the viscous term, you see that the ratio of this scale and that scale is precisely a Reynolds number. And the Reynolds number, remember, is large. So in that case, this term is also negligible because it's much smaller than this term. And so the only term that you have left is minus dp dy. So in the end, we can simplify all of this, our momentum equations, and we have the momentum equation in the x and the momentum equation in the y direction. So we can write them. The boundary layer equation for the momentum equation in the x direction in the boundary layer approximation is the following. So rho times our inertial term. The pressure term we keep, but in the viscous term, we only keep the viscous term with a partial derivation in the direction across the boundary layer, so normal to the uniform flow. So we don't have the second partial of u respect to x term. That is our boundary layer for the x momentum equation, a boundary layer equation. And for the y momentum in the y direction, we simply have that 0 is equal to our pressure term. So that tells you that across your boundary layer, you don't have pressure gradients. So the pressure is constant along the y direction. The pressure is constant inside of the boundary layer. Those here are the boundary layer equations.